welcome back to this course on C programming and assembly language. So we are in module 3 and we now are ready to get into the heart of this course, which is our ability to compile a given C program into assembly language, right. So let's start with a simple example. The task that is given to us is to compile the following C program into the respective object code or the assembly output, right. So when I say compile, I mean the task 2 that I discussed last time, right, which is to just generate the assembly output for this particular file without worrying about if what the other files contain and so on, okay. So what do I have here? I have int g underscore ivar, which is a global variable. The g underscore indicates that it's a global variable. Then I have the void main. I need a main for any C executable, which basically has a local variable int z equal to 0. Then z is basically the return value of a function fn, and I am passing two parameters to it, 2, 4, right. And then I am assigning the global variable g underscore ivar to z here, and I am done with that function. What does the function fn do? It's a function that takes two integers x and y as parameters, returns an integer, and this simply does the addition of the two parameters and returns the value z, right. So there are many interesting things that we first of all note here, and by the end of this lecture what we are going to do is we are going to put down a desirable set of features that we need, and we have to ensure that these features are retained when we translate these to assembly language, okay. So we need to pick up the right assembly translation that enables these features, okay. So the first thing we note is both the main and the function fn have this variable called z, okay. So which means that the variable z can be used in the same function in different functions with the same name, okay. This is particularly useful because imagine if this is in file f1.c and this is in file f2.c. Remember that when we compile, we do not even know what the content of f2.c is, right. So to keep track of whether these variables z are used even in that file is impossible. So therefore we need a way in which variable names can be local to a function, right. So g underscore ivar, for example, is not local, it's a global variable. That means across all the files I have to ensure that I do not have a repetition of that name, right, and therefore the concept of local variable is very good. Okay, these are my desired features. Right. So the next thing is that unlike the malloc and stuff like that, the developer really does not worry about where this variable z is stored or how much memory has to be allocated, whether it's going to clash with another location and so on, right. So all the developer is worried about is that when you enter the function fn, the local variable z in that function is alive, and when you are done with that particular function, when you return from that function, the local variable z of that function is gone, right. That's the key idea here. Only then I can use the same variable across two places without worrying about any clashes. So which means that the scope of variables, of local variables, is also very useful, right. And by scope I mean that this local variable z here is available only when this function fn is active and is being executed. So, the moment the instruction pointer returns back to the function main, that variable z should be gone, right, and it should not be accessible anymore. That is the idea, and that is the desired feature which is known as scope of a local variable, right. Now, you have the other things that you see are being used here are something known as function parameters, right. These parameters, okay. So, we need to make sure that our assembly code generation takes care of all these aspects very well. So, let us start with a very naive and an unoptimized assembly output, right. So, we already know what happens. For example, when we say that int z equal to 0, we know that this translates to move z comma 0, right. We will come to where what z is, where z should be stored and all that either in this lecture or at most by the end of the next lecture, right. Now, the next thing that I am doing is I am calling a function and passing two parameters to it, right. So, the function fn of 2 comma 4 is simply going to result in an assembly instruction called call, and that is going to be a fn underscore address. Now, what this exact address is and where this code for the function fn goes and sits will be determined only by the linker at linking time, okay. So, we are going to assign some label to this address called fn address for now. We will not worry about where this exact address is at this point of time, right. But before I call this function, remember that when I call this function, the program execution control goes into that particular function, right. Now, I need to pass two function parameters to it, right. So, the two parameters are 2 and 4, okay. So, what I need to do is I need to put some assembly code that allows me to pass function parameters, right. So, this how we pass these parameters and how they are used in the function are closely tied with each other. So, let us look at both of them together, okay. Now, let us look at the compilation of this f2.c, okay. The function fn is sitting in another file called f2.c, right. So, this move int z comma 0, right, is equal to 0 is again move z comma 0. So, note that the two instructions are exactly the same, right. These instructions are exactly the same between my two functions main and fn, okay. Now, I want to do z is equal to x plus y, right, which means that I am going to move into, let us say, EAX, right, comma x. I will move x into EAX, then add EAX comma y, lowercase y, and move z comma EAX, okay. When I do a return of z, what I really need to do is simply call the RET, okay. Note that all the red mnemonics that I am writing are actual assembly instructions, okay. All I need to now do is to decide what I have to put here, what instructions I have to put to pass parameters from one function to another. Now, because I am passing only 2 parameters, it may be natural for us to think maybe I could simply pass these 2 parameters through registers, right. For example, this instruction could simply be move EBX comma 2, move ECX comma 4, right, and then I am going to go into that particular function, right, Fn, where I need to access x and y, right. So, now it is possible, for example here, where before I start this function, if I simply said move x comma EBX or move y comma ECX, then it is quite evident that the function parameters 2 and 4 have indeed got passed to this particular function, right. It is possible, right. So, what I am saying is that before you enter and execute anything in that function Fn, you store these values of EBX and ECX into your variables x and y, right. They effectively become like some local variable, right, wherever they are going to get stored, and you free up the registers EBX and ECX. This is one legitimate way of doing it. However, the problem very clearly is that I cannot assume that I am going to pass only 2 parameters or 4 parameters or only as many parameters as there are registers that are available in the microprocessor, right. So, another desirable feature is I should be able to pass as many parameters as I want into a function, right. So, the assembly translation that we do should allow us to pass as many parameters as we want into a function, right. So, therefore, this straight away rules out depending on only the registers. So, the question is, what else can I do, right. So, let us go ahead and look at what we do with local variables first, and then we will see that function parameters are not any different, right. So, let us go ahead and look at local variables. Right. So, local variables essentially we have to ensure that the scope is maintained, wherein the moment you enter a function, that local variable is alive, and the moment you exit that function, the local variable is gone, okay. So, the question is, where do I store local variables? So, there are not many places that you can store these variables, there are only 4 segments that we have, right. So, we have the code segment, okay, the data segment, the extra segment, data segment, extra segment and stack segment. So, if I try to store my local variables in the code segment, it really does not make any sense, because if your instruction pointer happens to come to that location, then it will get interpreted as an instruction. So, therefore, straight away I do not think it is advisable to store anything in the code segment which is related to data. So, one possibility is to store the local variables either in data segment or extra segment, right. So, this is a possibility. Right. Now, let us look at the requirement that we had that we discussed previously, where we said that we liked the idea of a local variable, right, and we like the concept of a scope. Now the problem is, if you put something into the data segment or the extra segment, then the only way you can access these is by an absolute address, right. So if you want to access something in the data segment, data slash extra segment, absolute address, right. So basically I am going to say that, you know, I have to move an address, move into some, I will move EAX comma address of X, right, and then I could say that the contents of EAX, right, refers to the local variable X. Similarly, I could have another local variable ADDR, another address ADDR underscore Y, and that could, you know, refer to the local variable Y. Okay. So now again the problem is that when I have to do this, I cannot use these registers EAX, EBX and all that stuff to keep track of these addresses, right, because I need to use EAX, EBX, ECX, all the general purpose registers for my ALU instructions. So that is again ruled out. So then the question is, where do I put these local variables? So it turns out that the stack is a good place to do it, but let's look at an intuition or an intuitive reason of why the stack is the right place to put these local variables in. Okay. So we want to have the concept of scope, right. What is the definition of scope? The variable is alive when you enter the function, right, and dead when you exit. Or it is no longer accessible the moment you exit that function fn. Okay. So now let us look at, you know, what is it that happens when I enter a function. Okay. How do you enter a function? You enter a function by doing what is known as a call of fn underscore addr, right. So what does this instruction do? It basically loads the, of course it first pushes the return address onto stack, then it loads the EIP with the function underscore addr, okay, which means control is transferred to that particular location for execution. So when my EIP moves to that fn address and starts executing, I want my local variable of that function to become active, right. So the question now is, I need something to set a context for my new function when I enter, and the context to be reset when I exit that particular function, right. So how do you exit that particular function? You do a ret, and what does ret do? It does a pop of the return address into the EIP, right? It is going to simply pop the return address into EIP. So, what we notice here is implicitly when you call a function through the call instruction, the stack pointer ESP changes, right. This implies ESP and when you return, ESP is reset. So, every time a function is called, a push and a pop operation happens implicitly, altering the stack pointer ESP. So, therefore, there is a certain context that is set for us when we enter a function in the ESP, and the context gets reset when we leave that function through the return instruction. Therefore, ESP, right, is a good to keep track of a context, and this is what we are going to exploit in order to store local variables. And this is the reason that variables are stored on stack. So, now it turns out that function parameters, right, are also not very different from local variables, right. So, therefore, even function parameters variables, and therefore, these function parameters are also going to be stored onto stack before you call a particular function. Therefore, if you go back to the example that we discussed earlier, instead of moving, right, data onto registers before you call that function, what you would do is to simply push, right, 4 push 2 onto stack, right, because now I can do any number of pushes, which means that I can pass any number of parameters this way to a particular function. So, in the next lecture we will look at how you actually push these parameters onto stack before you call a function, and how exactly we are going to access local variables from the stack, and what instructions are necessary in order to consistently go from one function to the other and come back to the original calling function without causing any disruption.